have joined us. Is Alex Gravilescu with us? Don't see here. Okay, I think we're going to be going with a jury of 6 in this case. So let's get underway, shall we? Welcome along to the final for the online Young Physicist Tournament for 2022. Congratulations to the 3 teams who made it here. We have the teams of Singapore, China, and Canada vying it out for the title this year. I'll remind you that the scores that have taken place so far don't count from today. You know, everything, the round robin leading up to today was to get here. The winner will be decided on the scores that happen today. Okay, so we're going to be having 3 presentations and 3 oppositions, and we're going to be going through in the first stage where we're having the team of Canada presenting problem number 8, equipotential lines being opposed by China. Then we will have the team of China presenting problem number 1, invent yourself, being opposed by Singapore. And finally, we will have the team of Singapore presenting problem number 14, ball on membrane, being opposed by the team from Canada. Does that sound correct to everyone? I haven't said anything that surprised anyone then, I hope. All good, okay. All right, so we'll just quickly go through and do some introductions so we all know who we're dealing with. My name is Kent. I'm a physics teacher from Wellington in New Zealand. I've been involved with OYPT for about 15 years and the last few years with online tournament. And I'm really looking forward to seeing this fight today. Alan, what else do you say?
Okay, good luck to everyone. I am someone who's been involved with IYPT since 1998. As a team leader, as a IOC member, and for 7 years as president of the organization. I love IYPT and I can't wait to see what you're going to do today.
Thank you, Alan. Claire.
Hi, I'm Claire Byun from Korea, and I'm a professor in the Gyeongbuk National University in Korea. And I've been leading Korean team for past 10 years, and I've been also serving as an international jury on the IIPT for a few years. And it's good to be back, and good luck to everyone. Thank you.
Thank you. Gavin.
Hi, my name's Gavin Jennings. I'm a high school teacher from New Zealand. I've been involved as team leader and IOC member for New Zealand since 2007. Good luck to all of the teams. It's going to be an interesting final.
Alexander.
Hello, everyone. My name is Alexander. I'm from Ekaterinburg, from Russia. I'm a senior scientist at the Institute of Metal Physics, also a teacher at school, and I'm a team leader of Team Russia. I wish you all good luck.
Thank you. And Yungui. We cannot hear you at the moment. No, can't hear you at the moment, sorry. Okay, we might come back to that if we can. I'll just we'll go through the teams, and if we can give you a chance to have a look at that, and then we'll see if we can come back. We'll just get the team captains to just do a quick introduction from their teams. we'll start with the team from Canada.
Hello, everyone. My name is William Deng. I am the captain of Team Canada, and my team members are Jeffrey Lee, Alan Lien, Selena Guo, and Dennis Liu. And I wish both teams good luck in this match.
Thank you very much, and good luck to you too. And the team from China.
Hello everyone, this is Team China. I'm the captain from Team China. My name is Qingyi Wang. My teammates are Renqiu Ye, Shiyue Feng, Yiling Zhao, and Rui Wu. We're more than excited to be here in the finals with you guys, and I hope we enjoy the physics fights.
Thank you, and congratulations on making it to the final. And Singapore.
Hello everyone, I'm Shane. I'm the team captain of Singapore. Over here is Akshat. Over here is Luke. This is Phillips, and that's Rich. Good luck to the two other teams, and hopefully we can have a good fight.
Okay, thank you very much. Yonggui, did we manage to get your microphone?
Does it work? Hi, I'm Yonggi from Korea, and I was a team leader and also IOC member, and I hope you good luck. Thank you.
Thank you. All right, thanks very much. In addition to all the jurors and teams who we'll be hearing from today, we have a few people sitting in the background who are making this thing work properly. We have our flight assistants, Izzy and Danny, who will be running the clock and the scoring and making sure that I do everything I'm supposed to do when I'm supposed to do it. And someone who you may not have actually realized has made a huge part behind this, Felix, is the guy who has made all of the technical aspects of this work. The fact that we're all sitting where we are talking to each other is all thanks to all the work that he's done. So I think we need a round of applause for Felix before we get started. So well done, Felix. Okay, so now that we've got that out of the way, that brings us to the actual start of business. So our first round today is Canada being opposed by China. Now, being the final, the teams have selected the problems that they will present. And given that we do not need to go through the 1 minute of challenge time, so we will be hearing Canada present the problem number 8, equipotential lines. So you have 5 minutes preparation time, and can we please start that on the clock? And when you're ready to go, please let us know. We'll start presentation. And just at some point, if I can see the opposition has already done this, but if the reporter could put the name and the computer that you want to use just to make sure in the chat, just so we know we've got the right people.
Dev Digui Singe.
Okay, that's the name of the reporter and the computer that you want to use.
Oh no, the reporter is William Deng.
Okay, but maybe just someone put that in the chat. One of the team put that in the chat.
I've given one of the computers sharing right. Oh, there's 3 now. Presenter rights, I believe. . Let me know if that's not the right one, because there is like 3.
We got it now. Thank you.
You have about 30 seconds before needing to start.
All right. Hello, everyone. My name is William Dang, and today I will be presenting problem number 8, equipotential lines. The problem statement reads, place 2 electrodes into water, supply a safe voltage, and use a voltmeter to determine electric potential at various locations. Investigate how the measured equipotential lines deviate from your expectations for different conditions and liquids. So some relevant parameters I've identified for this problem include the electrode potential, the ion concentration in the liquid, and the electrode's rapid brief current due to the electric field of this battery. And as a result, the electrodes receive positive and negative charges respectively. And we know from Gauss's law that locations of charge are where the electric field has its sources and its sinks. And hence, this is why the phenomenon of equipotential lines occurs. So onto my experimental setup. Initially, I had my liquid in a glass basin and with some grid paper underneath it, and I used inert graphite electrodes held by 3D printed electrode mounts, and I used just a commercially available multimeter and would probe the voltage by hand. However, I noted that this system has very poor positioning accuracy and quite low signal-to-noise ratio. As a result, this motivated me to build an automated positioning system. So in my case, I use 3 stepper motors for X, Y, and Z motion respectively, and these are controlled using microstep drivers that interface using MATLAB and Arduino. This system, by contrast, has very precise positioning and has high spatial sampling frequency. So in this video, we can see the automated positioning system at work as it carefully sweeps across our glass basin, going up and then going down and sampling the voltage, then coming back up again, moving a little bit, going down, sampling voltage again, and so forth across the entire basin. So in order to make sure that this system is accurate, we need to calibrate it. So I use a digital dial indicator, and here are my 3 calibration plots for X, Y, and Z direction movement respectively, and we see that they have excellent agreement, which ensures that our system is very accurate to sub-millimeter accuracy. So instead of using a commercial multimeter, I also built my own voltmeter that's much better. So here I have my voltage probe in the liquid, and this voltage gets passed through a unity gain buffer and goes to my 16-bit ADC. And this is in addition protected by a 5.1 volt Zener diode. We note some statistics of this. So first, it has an input impedance on the order of a gigaohm, whereas commercial ones usually only have around a megaohm. In addition, the resolution is 0.15 millivolts, and the error is plus or minus 0.5 millivolts. And we see that this has an increased signal to noise ratio compared to the commercially available voltmeters. So onto my theoretical models. First, in my electrostatic model, I assume that there is an electrostatic charge distribution on the electrodes and in the liquid. I assume a quasi-2D geometry. I assume that the liquid is a homogeneous isotropic linear dielectric, and that there are no free surface charges along the glass basin's boundaries. So with these in mind, we can formulate our boundary value problem as follows. We have our liquid and our 2 electrodes fixed at 0 volts and 5 volts respectively. And then we also assume that the boundary has no free surface charges. And with these boundary conditions, we can write down Laplace's equation for the electric potential phi of xy, which says that its Laplacian is equal to 0 everywhere in the container. However, we note that this is difficult to solve analytically. So we resort to finite element method as a numerical solution of this, where in this picture, I show that we use a finer mesh near our electrodes in order to reduce the truncation error. So here's a comparison of theory versus experiment for distilled water. On the left, you can see the theoretical potential field plotted by solving Laplace's equation, while on the right, you can see our experimental potential field derived using our automated positioning system. But in order to actually see if they match or not, we need to actually overlay the two on top of each other. And so in this diagram, you can see that the dashed lines are theoretical equipotential lines, while the filled ones are the experimental ones. And we see that there is generally good agreement around the center of the liquid. However, there are deviations near the electrodes. So in order to explain where these deviations are coming from, we need to consider the notion of the double layer. So first, let me begin with a qualitative understanding of this. We have our water, a side view of it here, and some ionic compound like sodium chloride enters the water. Then the polar water molecules will dissolve the sodium chloride, and a solvation shell forms around each ion, dissolving the ionic compound. Then, when we place our electrodes into the liquid, the ions will get attracted to their oppositely charged electrodes and form a rigid, immobile layer of ions known as the stern layer. And with the stern layer in place, this actually attracts additional ions from the liquid that together form a diffuse layer, and the whole thing taken together is what is the double layer. So the reason this is relevant at all is that the double layer actually has very interesting behavior on the electric potential near it. Let me explain. So first, there is a shallow linear drop across our electrode just because it's an ohmic conductor. Then, right at the interface, there is a sharp transition across our stern layer, and the voltage drops very steeply, but still in a linear manner. This is followed by an exponential decay across the diffuse layer. So in the double layer model, we assume that ions are point charges, that the liquid is stationary, that there is a uniform temperature and permittivity throughout our liquid, and that there are no redox reactions at the electrodes, and lastly, that the double layer is always in thermodynamic equilibrium. So we begin by writing down our double layer ODEs. We first have Poisson's equation, which is just derived from Maxwell's equations, and we also have the Nernst-Planck continuity equations for this in particular. And where the notation here is that phi is our electric potential, C plus is the concentration of cations, C minus is for anions, and those are just some constants. And in order to qualitatively understand these otherwise difficult equations, we can consider an important parameter called the Debye length, lambda, which is derived from them. And this quantity characterizes how thick the double layer actually is, and it turns out to usually be on the order of nanometers. So in order to better understand how this double layer affects our potential far away from it, we will focus on how the potential behaves just across the center of our container. So in this simulation, the red line represents how the potential would behave without this double layer present. Whereas the green line, using the theory I just described, shows how this double layer affects the potential when it is there. In particular, we see that there is that steep potential drop across the stern layer, and that this actually affects the far field potential where our voltmeter can actually probe. So in order to explore this further, I considered varying the concentration of ions in my liquid. And to do this, I used an analytical balance. And when I vary ion concentration, in this case for baking soda for various concentrations, I noticed something very surprising, that there is actually an asymmetry between near the ground electrode versus near the higher potential electrode, and that this was actually not anticipated by my theory, which predicted that it should be symmetric. When I did this with table salt, I actually got very similar data, namely that there is an asymmetry not predicted by my theory. So I had a hypothesis for explaining this asymmetry. I realized that sodium cations have a smaller ionic radius than both bicarbonate anions as well as chloride anions. And in addition, because we know the electrodes obviously have a finite surface area, this implies that there exists a packing limit for the number of ions in the stern layer that can physically pack onto the electrode. And this actually affects the potential because the rise or drop of it across our stern layer increases with a greater ion packing density on it. So in order to explore this further, I consider my final theoretical model, the ion packing model. So first, I note that the double layer can in a way be viewed as a capacitor, since our electrode is like a resistor, and then the double layer, formed by the stern and diffuse layers, are like two capacitors in series. Then when ions pack onto the electrode, they induce a leakage current in the form of electrons away or towards the electrode. And in order to measure this tiny leakage current, I built the following circuit. So we have our leakage current that goes through a transimpedance amplifier acting as an IV converter, and this then goes through an RC low-pass filter that goes through a unity gain buffer, and finally to our 16-bit ADC that's protected by a Zener once again. I know that this setup has adjustable sensitivity, high signal-to-noise ratio, and can resolve the transient current. So onto my cyclic voltammetry measurement. What do I do here? Well, I apply a low-frequency AC triangle wave across the electrodes with a peak-to-peak potential window of a volt. And then I note that the leakage current resembles a capacitor's charging and discharging curves, and this actually reflects the presence of the stern layer. So in real life, my setup is as follows. I have my function generator that supplies this triangle wave across the electrodes, and this is processed by our leakage current measurement circuit, which is then read through the oscilloscope. So when I do this, what happens is, for varying concentrations of baking soda, when I increase my voltage, the leakage current goes up, and similarly, when it goes back down, it decreases. But the important thing to take away from this is that there is a saturation of the leakage current, and this actually indicates that there is ion packing in my system, because the packing limit has been reached and there is no more leakage current being formed past a certain voltage. So to quantify this, I introduce a dimensionless packing parameter defined as the ratio of the average molar concentration to the maximum possible concentration you could get, assuming a cubic packing. And with this packing parameter, we can modify our previous equations, and we note that comparing the theory using these modified equations versus our experiment, we see that there is still a bit of deviations due to the covalent nature of methanol, which I used in this case. But for the other two, the blue and the red curves, there is good agreement because both of these are ionic compounds, and the double layer is a property that is peculiar to ionic compounds. And so this also illustrates a limitation of my theory. So onto some key parameter interactions. First, we know that as ions get bigger, the amount of ions you can pack decreases. And then, but as you can pack more, the maximum potential drop you can observe increases. And as the maximum potential drop across the stern layer you can get increases, this actually increases the amount of deviation you can get. So these three plots taken together show that the ionic radius imposes an upper bound on the amount of deviation of equipotential lines that you can get. And this is the fundamental insight of my research that I did not encounter anywhere in the literature. So in conclusion, I have offered a thorough qualitative explanation of this phenomenon. I have gone through my thorough experimental setup, my thorough theoretical models for modeling this phenomenon, and finally, thorough experimental verification of my theoretical models. So here are my references, and thank you for listening.
Thank you very much. Hey, the opponent from China, you now have 2 minutes to ask clarification questions.
Okay, hello, Willem, and I have several questions for you. Please answer them concisely, thank you. So my first question is to clarify that your boundary condition is that there are no free surface charges on the boundary, is that correct?
Yes, this is correct.
Okay, the next one is that did you assume electrostatic condition throughout your system?
I assumed it in my first theoretical model, but I know it's not actually electrostatic, which I account for in my later theoretical models.
Okay, and what is the time scale for experiment?
It usually takes around an hour.
Okay, that's pretty long. We'll get to that later. And the next question is that what is the order of magnitude of the leaking current you measured?
Oh, it's around a milliamp.
Okay, let me note that. Okay, thank you. And what is the voltage you applied to your electrodes?
5 volts, but we vary
In all
it.
the experiment? Okay.
No,
5 volts?
so
Okay.
in the prelim, yes.
And what about in the quantitative experiments?
So we vary it, but like as I showed in my first theoretical
Okay.
model, it was initially set at 5 volts.
Okay, we'll get to that later. And what is the depth of the probe that the probe reaches in your experiment measurement?
It always goes to the bottom of our glass basin.
Okay, to the bottom. Okay. And what is the time it takes to measure, like approximately for each of your data points?
It takes around 1 second.
Okay, that's pretty quick. We'll get to that later. And finally, about the packing parameter you derived of your own, which is quite impressive. What parameters is it correlated to?
This packing parameter, as you can see from the definition, is just correlated to the ionic radius of your ions.
Okay, I think time is up. Thank you.
Thank you. Okay, you now have preparation time of 5 minutes. Then you have about 30 seconds remaining. Remember, you have to be ready to start at the end of that time.
All right, we will start in a short second. So can everyone see our screen share right here?
Yes, we can.
All right, dear judges, fellow contestants, this is Qingyi Wang from Team China, and we're going to start our opposition speech on problem number 8, equipotential lines. So from the problem statements, we derived several tasks that we believe the reporter needs to fulfill, including to theoretically calculate equipotential lines in different conditions and visualize, and also to design a suitable experimental setup to draw equipotential lines, as well as to quantify the deviation between experiment and theory. So in a summary of the report, his theoretical model has a very thorough calculation of potentials in the finite system, and his simulation successfully reflected his suggested deviation, which is on the Stern layer. His experimental research investigated two parameters, type of liquid and the concentration. His automated positioning system has produced data for comparison with the simulation to some extent. For the deviation analysis, which the problem has asked for, he quantitatively addressed the deviation, which is a double layer effect, and he quantified the far-field impacts of the Stern layer. So in his theoretical analysis, we have some strength, identified some strength here. For example, he used the simulation to solve the Laplace equation and produce a simulation graph, and he introduced the packing parameter of his own. He explained the deviation and considered two parameters. And also, we have some areas of improvements for him. For example, we wish he can demonstrate more equipotential lines, especially in comparison with his data points, as well as we hope that he can characterize the current in the liquid and the water electrolysis and its effects. He has produced a quasi-2D, or rather one-dimensional analysis of a 3D model, which we believe is inadequate, and he lacks clarification for the electrostatic system, which we will get to in talking about his experiments. Also, he had no investigation into the shape of the electrodes, which we believe is quite important according to his theory. In his experimental research, we identified these strengths, including a very fancy setup system, and he also calibrated it, and he considered quite a lot of details, also produced data graphs for them in the comparison, and they match with his Stern layer modification. In areas of improvements, we hope that we can clarify his measurement method and his circuit in the discussion. Also to consider the cause of the, the cause of the leakage current and what the leakage current really means. Also to investigate the time scale and the static state in his system. We also hope to address the covalent compounds, which was not really relevant to his theory, but we hope that he can produce a qualitative explanation. So here are some of our suggestions. First, as the reporter only used the Poisson-Nernst Planck equation on the x-axis, we hope that he can expand to the y-z axis and put them into simulation for a more adequate result and modeling on this entire system. And he can also explain theories of double layers for covalent compounds. Does it really have double layers in this case? I'm not so sure, but we can talk later. He can also more accurately model for the voltmeter and probe, which he built himself in experiments. We hope he can enlarge the scope of the experiments, consider several other parameters, including the size, shape of the container, discuss the potential at more locations rather than the one line across the container, also to investigate the position and material of the electrodes. And these are the discussion points we'll cover later, including the size and the effect and cause of the current in the system, the current after steady state, also the electrostatic conditions and his capacitor model for the Stern layer. We also wish to clarify the source of leakage current and his packing parameter calculation, as well as the influence of the liquid height, the equivalent resistance, and the voltmeter resistance. So this is all of my report, and we hope we begin a wonderful discussion. And now, could the reporter share his screen?
Yes. Oh, I need sharing rights.
All right, we're good. So first, I wish to clarify about the electrostatic condition that I mentioned earlier. So in your theory, do you believe that after a long time, all the ions are packed at their respective electrodes?
So in this electrostatic like model, right, it's just like a simple model. It's not actually electrostatic. There's like constantly as I mentioned, like leakage current being induced by these ions that are present.
So what is the leakage current precisely? What are they from?
It's for electrons. Electrons, like the ions come onto the electrode, right? And if it's like cations positively charged, then they will attract
Yes.
electrons onto the electrode. That's leakage current. Or if it's anions coming onto your electrode, they will repel electrons. But either case, that forms a leakage current.
Do you mean that the electrodes come down from the outer circuit and into the liquid? I do not believe that is possible.
No. Electrons stay in
Okay.
the electrode. They do not like go into the liquid.
Okay, so did you account for the electrolysis of water? I believe this might have contributed to the leakage current.
Okay, so regarding that, here I showed that the electrodes I use in my experiments are graphite electrodes, and that means that they are chemically
Yes.
inert. But graphite is still a good conductor, so that's why this is ideal for the
Yes.
experiment. We don't get electrolysis, so we don't need to worry about it.
Okay, I think graphite is actually a pretty good choice. But let's talk about the ion diffusion you mentioned that happens outside the Stern layer. So does the ion diffusion happen throughout the experiment, or do they stop at a certain point?
You mean the diffuse layer or the diffusion of ions
Yeah, the
throughout the
diffuse
liquid
layer.
in general? The diffuse layer. So this happens throughout continuously because the Stern layer is made of immobile ions. They're rigid and they can't move. But these diffuse layer, the ions are not like held as like firmly, and therefore they can just move around.
So there are still several, like some ions to some extent inside the liquid.
Yes.
That are in motion, right? And I see that in your comparison with experiments in the, can we go to page 29, I suppose? Yes, this permittivity you mentioned here, I believe that is the permittivity of pure water. So I think this might be inaccurate to some extent.
This is just taken from literature. And was
Okay,
for the
maybe
purpose
you
of
can
the
try
simulation.
to, all right, you can try to verify that a little bit. So, so this value goes into the simulation.
Yes.
All right, I think we're good with that. And so about the Nernst-Planck equation, could we go to that page? Yeah, so I see that you accounted for the x-axis here, so which is the line that is that cuts through the container.
That is correct. Yes.
Yeah. So does this really correspond to your experimental setup?
So like in this picture right here, right, like if we go very close to our double layer, you could effectively treat it like an infinite sort of like plate, and therefore the variation of the potential along near the double layer can essentially be approximated along one dimension because the other two dimensions are like essentially negligible.
All right.
But if you wanted to incorporate you could replace second derivatives everywhere in this equation by the
I'm aware of this
Laplacian
method.
and corresponding like divergence and
All
so
right.
forth, and extend it.
Great,
to
I'm aware
3D.
of this method. Okay, thank you. And could I see your quantitative experiment setup and the electrode you used?
So you want to see like this, for example?
Maybe the page above it, or yeah, this one's
here?
your quantitative experiments, not preliminary. Maybe on around page 40 or 39 somewhere.
Oh, okay.
Yeah, great. Page 40. So your electrodes are plates here. Is that correct?
Yes.
So did you place them on the like really close to the boundary of the container, and that's why you treat it as a quasi 2D model?
So that's just for the first theoretical model, as I emphasize again. But in this picture, the electrodes, yeah, they're placed about like 6 centimeters apart from each other. And we know that they are at the same distance from the edge of the glass basin because we use precisely 3D printed electrode
that's a good
mount.
choice of location.
What is
the width? I would like to ask, what is the width of your electrode and what is the width of your container?
It depends on which electrodes we use. Like mostly we stuck to just point electrodes, but if you use plate electrodes, I have some data in my appendix that shows how the
Great.
potential looks
see
for
that.
plate electrodes. And in this case, the width is usually around 4 centimeters. But for the plate electrodes, I show here that the plate electrodes, you see they have a 2 millimeter diameter.
Okay. According to this, I suppose that especially the cylinder electrodes cannot be taken as a quasi-2D model here, which actually their potential distribution cannot be simplified to that way. But with your plate electrodes, I think if the plate is wider, like they're almost the same width as the container, I think that can be treated correctly. So my other question is that your regarding the shape of your electrodes. Can we go to your packing parameter? Yeah, right here. So could you just quickly explain to me how do you calculate the Cmax here?
Cmax. So this is just the maximum ion concentration you can have. So if you imagine like number of ions basically, or number of moles of ions per meter cubed of space. And if you assume it's packed densely in cubes of just ions, like these spheres right here, then this formula just comes out.
Okay.
It's like,
so
yes.
So I'm actually quite confused why this packing parameter has nothing to do with the parameters of your electrodes. I believe that different shapes of electrodes might create different packing patterns.
Actually, I would like to disagree because the packing parameter is closely related, as the number of ions that you can pack onto a given electrode is influenced by the electrode surface area, and therefore it's of relevance in the theory.
I would disagree with you on that one, but let's move on to another point, which is your graph for the methanol.
Methanol?
Yes.
I have
there
a
were
graph
quite
of
a lot
it in
of
my.
lines.
I have one in my appendix, but no, not this one. I think you mean this one.
Yeah, the one. Yes,
Okay.
this one. So I understand that you did not theoretically account for these covalent compounds, but could you just qualitatively explain this deviation here?
All right, so the double layer, as I explained qualitatively in my report, is when an ionic compound specifically will dissolve in water, and then the solvated ions go to their oppositely charged electrodes. But the thing is that covalent compounds, they don't dissolve the same way as ionic compounds do in water. And as a result, this double layer effect is not as prominent. Nonetheless, with some covalent compounds, such as water, you still get a bit of ions in the form of like hydronium and hydroxide ions. The pH is 7, right? So the concentration is like, yes. So you can still get a small effect like this. It's not as prominent.
So do you mean that for polar covalent compounds such as water and methanol, there is still double layer present, or is there no double layer at all?
There is still, but it's very minimal. And because it's very low concentration, the packing limit is quite difficult to reach.
Okay, I'm good with that. And can we go to page 30? Sorry, page 31, sorry. Yeah, now 32, sorry. Yeah, so we see on the right part that you circled, the red dots and the orange dots actually cross each other. Do you think that represents anything?
This could just be due to small experimental fluctuations, but you see the general trend is still very clear, that there is a large variance on the left side and a smaller variance on the right side. And this is because the sodium ions on the left side are smaller, so then it hasn't reached the packing limit.
I understand that explanation you presented earlier in your report. Maybe you can produce some error bars and multiple experiments to minimize the errors there. And my final time scale, final problem, I would like to go back to the time scale we mentioned earlier. You mentioned that for each data point, you spent approximately 1 second on it. Do you think that is enough time to allow for the liquid and the electric field to go back to the static position?
Because let me go to my video again. So our electrode.
I'm sorry, just going to need a very quick answer. Time is actually up. Do you think that is enough time or not?
Yes, I think it is enough time.
Okay, thank you. All right, thank you for that discussion. The opponent, you now have 1 minute to make concluding remarks.
All right, hello everyone. Here goes my opposition conclusion. So in our discussion, we discussed with the reporter about first the leakage currents which come from the ions, and I will believe his characterization and the value of the permittivity is still not correct. He needs to take ions with water ions in the water into account. Also, the shape of the electrode, as mentioned by the reporter, is actually a key parameter here. We believe that the quasi-2D or rather just 1D model is not really accurate here, and we suggest that he add a 3D model to the simulation, which can be done quite easily by modifying the Nernst equation. Also, the reporter addressed the covalent compound, which produce minimal double layer. We are good with that explanation. And finally, about the last problem, we didn't have time to finish. We believe the time scale in his experiment, as well as the time it takes for each data point, is not really appropriate for the liquid as well as the electric fields to go back to their static conditions, which means that his theory and experiments do not match well. And that's all of my report. Thank you for the discussion.
Thank you
all
very
right,
much.
I would like to. Oh, all right, I
Kate,
would
you
like
have
to
2 minutes.
I'd like to thank the opponent for having had a very productive discussion on my report. So first, we went over my electrostatic assumption, and the reporter said it is not accurate because there is a leakage current, and I agreed with the reporter, but mentioned that this was only my preliminary theoretical model. And my whole presentation, the purpose of it was to sort of disprove this and provide additional insights with the ions in the water and how the way that they are non-electrostatic contributes to the deviations. Next, we clarified the concept of leakage current, where I explained that it's just electrons attracted to or repelled by the ions that are forming the Stern layer. After this, we went over the electrolysis of the water that could occur, but I explained that this was not an issue in my experimental setup because I made sure to use graphite electrodes, which are inert. Finally, we talked about the diffuse layer, and I explained that ions in this layer are constantly mobile. By contrast, the Stern layer ions are stationary. Then we went over my Nernst-Planck equations, and the reporter said that my one-dimensional equations were not adequate. However, I believe that they are adequate for sufficiently close distances to the electrodes. Next, we looked at my leakage current measurement setup, and we discussed the distance between my electrodes as well as the dimensions of the electrodes. And in both cases, I told the opponent that I believe I had a very accurate setup due to the precisely printed 3D electrode holders. And after this, we talked over my packing parameter and my calculation of the maximum ion concentration, which I explained was due to a cubic packing of ions in the liquid. And finally, we went over a qualitative explanation of covalent compounds and how they manifest with regards to the double layer phenomenon. And again, I thank the opponent for having had a very fruitful discussion. And yeah.
Thank you very much. Okay, we now move on to the jury question stage. So if I could ask the jurors to turn their cameras back on. I will also ask the jurors to try and keep these questions short. Should be a short question to ask and relatively short to answer. They're clarification questions, not large discussion questions. So, does anyone like to get us started? Alex.
Please, a very short question for the reporter. What was the depth of your basin, and did you change it during your experiments?
The depth of water was held at around 4.
Gavin.
Question to the reporter. Can you please just tell me what was the purpose of the function generator?
The function generator was just to apply the AC triangle wave across our electrodes that I needed in order to conduct my.
That's fine. And what frequency did you choose, and why did you choose the shape you did?
All right, so the frequency we chose was as listed here, 0.1 hertz. And the reason for doing this is that this is actually a very well-known technique from literature.
Okay, and the shape, so 0.1 hertz and the shape?
Yes, it's from literature that this shape will generate an interesting IV plot that
Okay, so you didn't vary the shape even though you had a function generator.
the purpose of it was to prove the presence of ion packing in our
Okay,
system.
thank you.
Okay, can I ask the reporter? I just wanted, I may have skipped over this quickly while I was writing something down, but does you have any justification for your assumption of cubic packing as opposed to any other form of packing?
So it is possible that in real life there could be some other packing, but a cubic packing is just simplest mathematically and is representative of ions trying to minimize their interatomic potential energy.
Okay. Kevin?
Another question for the reporter. Can you just confirm, is there a current actually in the liquid?
The current in the liquid is essentially just ions diffusing through it, and this is on the order of a milliampere.
Though you've got a triangle shape, so when does this milliampere occur?
Oh, as you see in my plot here, on the y-axis, it goes up to about 1,000 microamperes, and that is 1 milliampere.
But you haven't confirmed the shape of the pulse that you're adding is a triangle.
Yes.
So when does the milliamp occur?
Oh, it occurs when the voltage reaches the maximum. So 1 volt in our case. Or sorry, 0.5 volts, because we sweep from negative 0.5 to positive 0.5.
Okay. And last point on clarification here, all of your potential differences only seem to be measured to 1/100th of a volt. Why is this?
To 100th, where, sorry, do they seem to be measured to 100th of a volt?
Well, on your plots earlier on, you were having plots like 1.50 volts and this sort of thing.
Sorry, I'm not sure which plot you were referring to.
Okay, we'll leave it.
Can I please ask the opponent, do you consider that this was a one-dimensional or two-dimensional analysis or three-dimensional analysis? How many dimensions do you think were actually analyzed in this report?
We think we should do a full three-dimensional analysis because we believe that the potential varies in different depths.
How many do you think were actually done?
So, pardon?
How many dimensions do you think the report actually analyzed?
I think he analyzed one dimension, which is the line he mentioned in many of his plots.
Okay. Any other questions?
One last question from me, perhaps. Just to the reporter, finally. Can you just confirm, does the concentration of the ions in the liquid change during your experiment?
No, this does not.
Quick question then to the opponent. Would you think the ion concentration would change, and if so, why?
I believe the concentration varies at different locations because there is electrolysis of the water and of the solution, as well as the system is actually not electrostatic.
Okay, we're out of time for jury questions. Okay, so we will go through our normal system of allocating grades and entering them in the system. However, once they are entered, we will not be announcing what the scores are, just to remind you, but one of the flight assistants will let me know who the high and low scores were, and we'll ask for some feedback from them on why they gave the scores they did.
I think all the grades have been submitted.
Okay. Yes. The grades have been submitted. Now, just for some comments, I'm going to ask. These are not any. These are in no particular order as well. I'm going to ask Alan to make a comment for the reporter, please. Your grade. Not what your grade was, but just why you gave it.
Okay, I thought the reporter did a very good job. I thought a lot of consideration was given to his theory and his experiments were well developed, but I think the reporter challenged the ideas of 1D and 3D very well, and that influenced my decision.
Thank you. Yes, I'm going to make a comment as well, and yes, I thought that there was a lot of very good stuff done in there. A lot of things that were very well considered. The 1 and 2D, 3D sort of thing, I was just sort of struggling with what did seem to be a 1D analysis. How you can have a concept of equipotential lines in one dimension. Seemed a little bit difficult to follow there. But otherwise, I thought it was a very good presentation.
Me too.
For the opponent, could I please ask Claire to make a comment? You're still muted, Claire.
Sorry. Okay, the opponent first start with very short, good questions and manage the time very well and represent the presentation and in the speech very well. But in the discussion part, they kind of threw out lots of questions, and most of them are valid, and they ask the question they supposed to ask. But as far as the impact goes, they wasn't like a strong impact on any of those questions. So I was just stopping there.
Thank you. And again, I'm one of the extremes. So for the opponent, yeah, I thought your questions your questions and speech were really well done. That's probably the best use of those that I've seen in this tournament. And anytime I thought of something to ask, you asked it before I did. So yeah, I thought you did a really good job with that. So yeah, well done. Okay, that brings us to the end of stage 1. So we'll have a short break. So it is now 7:15 where I am. So we'll have a 10-minute break, and we'll aim to be back ready to go for stage 2, which will be China reporting Invent Yourself being opposed by Singapore. And if we can please be back ready to start at 7:25, well, 25 past the hour, wherever you are. Thank you very much. waiting for one more juror. Okay, I think that's all of us here. And we have our flight assistants with us. Jamie, Izzy.
Yeah, I'm still here.
You?
Danny's giving a thumbs up.
Okay. Okay, so that means we're all ready to go for stage 2. So in stage 2, we have the team from China as the reporter, presenting the problem Invent Yourself and being opposed by Singapore. So we can now start the clock for 5 minutes of preparation time.
Okay, hi everyone. I'm Yilin Zhao from Team China, and before everything gets started, I want to confirm that my voice works properly. Can you hear me, please?
Yes.
Okay.
You?
Thank you very much. Yeah, I see it. And if there are any internet issues when I get disconnected, my teammates will be there to help. So if I get disconnected at any time, somebody would, can you just remind me in the chat box so that I can switch to other devices?
Absolutely.
Okay.
Thank you.
Thank you very much. And I'll try to share my screen, and I will start when the 5-minute countdown stops. Yeah, I'll try to share my screen. Okay. Can you see my screen sharing?
Yes.
Okay, well, thank you so much. And I'll be in the state when 5-minute countdown stops. Thank you.
You have about 20 seconds until you need to start.
Okay, hello everyone, can you hear me? And I'll start my presentation now. Thank you for your waiting. And the problem I'm going to present today is the first one, image yourself. Now I should create a non-invasive device that determines the direction of fluid flow inside an opaque pipe. And I should also optimize my device so that I can measure the smallest flow as possible. So in my overview, there are mainly 5 parts of my research, and let's go to the first part, introduction. Let's first talk about the independent variables. It's very easy because it's simply the direction of flow inside the pipe. And when thinking about the dependent variable, we need to answer one question. What could changing the direction of the flow affect? It can affect 3 things. The first thing is temperature distribution. The second thing is sound waves propagation speed. And the last one is the Hall effect. From all these 3 methods, this one will be our preference. But any pre-experiment, we are going to go through all these methods and take a look at all of them. The first one is measuring the Hall effect. When molecules carrying charges is moving in a magnetic field, it will deflect, causing an electric field. And then the electric field will cause a potential difference called the Hall difference, which is proportional to the flux. And by using a Hall element, we can measure the flux of the fluid inside the pipe. And by deploying the Hall effect detector, the fluid must carry charges. However, not all fluids have charges like air we have here. And the second way is to measure the time or phase difference of sound waves traveling in the same or a different direction as the fluid. The mechanism is very simple. The propagation speed of sound waves along the direction which the fluid moves become faster, and the opposition direction gets slower. And by using this device, we are able to measure the flux as well. And by observing the results, when measuring the flux of water with impurities, this one, we're not able to attain the data. You may ask the reason why. The reason is that impurities in water deflect sound waves, causing measurement error. And let's take a look at our selection of determine the direction of flow. Now I should heat a part of a pipe, okay? And the phenomenon is manifested by the temperature difference of the upstream and downstream part. As we can see, the temperature downstream is higher than that in the upstream. And the red indicates high temperature, whereas blue and green indicates low temperature. And we have our data here. After calibration, the thermal flux meter is very accurate. Its performance makes it the best selection for further investigation. And now I also have a video here showing the temperature of upstream and downstream, as you may see here. And now I have a specific picture from the video which showed that the temperature upstream is 19.2 degrees Celsius, and the downstream is 21, which the temperature downstream is higher than in the upstream, and it conforms to our expectation. In a theory, we're gonna describe the temperature field quantitatively. Here's a diagram of the control volume that we selected. The red part is a heating wall, the brown one is a tube, and the gray one is a fluid region. First of all, we do the meshing part. We put them into very small parts, and then we're gonna find a very small volume element and then execute the energy balance analysis. The main direction for heat transfer is in the x-axis, including advection and diffusion. The advection equation is symbolized by this one, whereas the diffusion equation is symbolized by this one. And also, both the surface at the top and the bottom of the finite volume element will transfer heat as well. So there will be heat transfer in a vertical direction as well. And it could be symbolized by the following equation. And then don't forget that our heated wall is very hot. So along with the heat generation equation, this one, we can combine these things and get this PVE. And by solving these PVE, we get this result. However, this is not very obvious. So let's take a look at the graph here. If we take a look at these graphs carefully, we will see that it's basically in a very symmetrical shape. However, the temperature on the right side, which is downstream, is higher than that on the upstream. So that by selecting 2 symmetry points here, we can detect the temperature difference, and then we can get the direction of flow inside the pipe. And this is basically how it will work. We have drawn another diagram which conforms to our theoretical results here as well. And what more can we get from PVE? By looking at our results, we can see how these variables have a relationship with the overall performance of this apparatus. And the results from the theory will be validated later. And in the experiment, we have used 2 things. First one is ANSI simulation, and we have also performed actual tests. And in the simulation experiment, we use the fluid flow module from ANSI to perform simulation tasks. First of all, we import the 3D model. This part is a heating part, and this one is a flow, is a tube. Okay. The second one, we do the meshing, And then we'll have our calculation set up. This is the inlet, and this is the outlet. And then we'll have our results. Red one indicates high temperature, blue one indicates low temperature, and this one, transparent, indicates lower temperature. Okay, and we can also get a temperature distribution of the tube as well, which, as you can see, has a very fair coupling with our theory. You see we have two lines here. Okay, and we have also done some very interesting trials as well. For example, the hot filled tube, because in many cases, the tube and water, the air and water in the tube are not completely mixed up with each other. So we will have this occasion. And then we have a mixed fluid tube. And in this case, it is alcohol and water mixing together. And the data will be presented later. And in our actual experiment, we have a picture of diagram here. We have two temperature detectors, this one, and we have the heated wall, and then a thermometer which detects the temperature difference between two symmetry points. And then we'll use thermal detector instead of thermal imaging in our actual experiment. And we also have pumps, and we have an K temperature detector in an insulated shell. So we will go through optimization process, and then we will test its performance under various scenarios. The optimization part includes the position of the detector, best time for measurement, and heating temperature, and the testing performance includes many other things as well. So first of all, let's take a look at the temperature detector's position. Where should we put it? Okay, by looking at three results, the theoretical results here, the simulation results here, and the actual results here, we can see that these three things have a fair coupling. And in a conclusion, the temperature detector should be located at a distance of 25 centimeters away from the heater, at which the temperature difference reaches its peak. And the second optimization is the best time of measurement. Okay, this is the graph we have here. We can see that the general trend is that as time elapses, the temperature difference first increases to a peak and then slowly graduates, decreases for a slightly little bit. That's because as water takes away the heater responds by having a slightly increase in heating power to maintain the proper heating temperature. And then we can determine that the best measurement time is at 0.5 minutes, at which the temperature difference reaches its highest. But any time after 0.5 minutes would work as well, because remember, what we are going to determine is the direction of flow inside the pipe. And then what is the best heating temperature? Okay, we heat the wall at 305 Kelvin, and the minimum flow measurable is 0.5 cubic centimeter per second. And if we rise up the temperature for a little bit at 310 Kelvin, the minimum flow measurable is 0.3 cubic centimeters per second. And if we rise up the temperature for another 10 Kelvin, the minimum flow would only have a little increase of 0.2 cubic centimeters per second. And here is our result. The heating temperature of 310 Kelvin is preferred and has several advantages. The first one is accurate, and then the heating temperature is low so that there will be no phase change for fluids, and it's also fast to reach thermostatic condition. And it can be readily explained by our theory, because as heating temperature increases, the power of heating increases, and T increases as well. So as T increases, the difference between the two symmetry points, the temperature increases as well. So it leads to an enhance in the performance. And also, we're going to change the fluid moving inside our pipe. And we use fluids with different thermal conductivities, and we have drawn a graph here. And as thermal conductivity increases, the minimum measurable flow decreases. And it can also be explained by our theory, because the thermal conductivity of the fluid responds to K here. And as K increases, the difference between gamma 1, 2 increases, results in a more difference between these two symmetry points. So it's also proportional. And also, how about changing the diameter of the tube? How would it affect the overall performance? Okay, take a look at these data points. We can see that as the radius of the tube changes, the minimum measurable velocity is not affected. Okay, how to explain this one? It's quite easy, because if we scale up the tube for like 100 times, we'll see that no physics attribution of the tube actually changes. So the radius of the tube will not affect the minimum measurable velocity. Okay, and it can also be confirmed from our theory, because this result has got no relationship, has got no relationship with the section area of the tube. And then how about changing the tube's material? Okay, we have used tube material of different thermal conductivity. And we can see that as the thermal conductivity of the tube increases, the accuracy actually decreases, because we can see that the minimum measurable flow increases. And it can also be verified from our PDE result, because as Ks increases, gamma 1,2 decreases. So the difference between these two temperature symmetry points decreases as well. So it will lead to a decrease in overall accuracy. And how about changing the tube's thickness? Okay, as we make the thickness of the tube higher, the accuracy decreases. It's very easy to explain that, because if we make the thickness of the tube infinitively large, then we will not be able to measure the direction anymore. So how about using mixture flows? We have drawn a fancy animation here to better illustrate the. And it has a linear, the minimum measurable flow has a linear relationship with the volume ratio of air and water, meaning that when measuring mixed liquids, we could treat them as a homogeneous mixture of both. So, as a summary, we will have an introduction on the usage of this apparatus. The first thing, power on, and then turn the heating temperature to 310 Kelvin in room temperature. And then pull the temperature detectors 25 centimeters from the heater. And then turn on the fluid and let it flow. So as it flows, the temperature downstream is hotter and the temperature upstream is colder. And by detecting the temperature difference, we can see the direction of flow inside the pipe. Success for our apparatus. And then we suggest using thin tubes and tubes with low thermal conductivity, which is plastic. Well, for example, plastic. But in other conditions, our apparatus works just fine. It is just an optimal setup. So to conclude, our best heating temperature is 310 Kelvin, accuracy is 0.3 cubic centimeter per second, and the detector's distance is 25 centimeter. As the material's thermal conductivity rises, the more accurate the apparatus would be, and as the tube's thermal conductivity increases, the less accurate the apparatus would be. And the tube sectional area has got no effect on the overall accuracy, and as tube thickness increases, the less accurate it is. And for mixture fluids, we can treat them as a homogeneous mixture of both. And one thing I want to mention is that the problem says we are going to determine the direction of fluid flow, which is less concrete. It's less concrete than measuring flux, but actually, our apparatus is so like accurate that we can really measure the direction of flow at a very low flux. Okay, so that is for my conclusion, and here is my references. Let's take a look at this animation again, which shows the basic mechanism of our apparatus. We have a heating wall, and the temperature upstream here is lower than that on the downstream. And thank you very much for listening.
Thank you. Okay, the opponent, you now have 2 minutes to ask clarification questions.
Thank you, reporter, for your report. Could I ask, how do you define the minimum flow rate? Because you mentioned it was 0.2 cm³ per second. How is that defined?
Actually, it's 0.3. It's 0.3
yeah.
cubic centimeters per second, and it's at the best heating temperature of 310 Kelvin. Our accuracy is 0.3. It's 0.3 cubic centimeters per second.
So how do you know it as 0.3?
Yeah, it's a very good question. I can explain it here because, as you can see,
okay.
at the
I think we can discuss this further. So sorry,
Okay.
to move on. How do you assume that the cross section of your water has a uniform temperature? Like the middle of the pipe has the same temperature as the outside?
Well, I don't think it has a uniform temperature, but it will not affect our overall accuracy.
Okay, so how do you measure the temperature of your heating element?
Excuse me? How do I measure the temperature of what?
The heating element, so your T0.
Okay, we have a temperature detector at the heating wall.
Okay, yeah, thank you. So, do you consider the heat loss from the pipe to the surrounding?
Definitely, that's the core of our.
Which equation do you use?
Sorry.
Which equations do you use? Do you have a slide for that?
Yeah, right. Okay. We have slides in the theory part as well.
Okay.
We have our advection, diffusion. Yep. And the.
So, for the simulation you used to compare with your experiments, right? Was that self-coded using your equations, or was that used from the fluid element mesh you
It's from the fluid element mesh.
Okay, thank you. So for slide 40, are your temperature sensors equidistant from the center of your heating element?
Sorry?
For slide 40, are your heating elements equidistant from your temperature sensor?
Yes.
Sorry, from your heating element. Okay,
yes.
Thank you.
Thank you very much.
So for slide 46, how do you derive those error bars?
Sorry, we're out of time. Okay, you now have 5 minutes preparation time. We have about 15 seconds.
Can everyone see my slides?
Yes, we can. Okay, you can start your speech now.
Okay, so hello everyone. My name is Shane Jindal, and today I'll be opposing problem number 1, Invent Yourself by China. So as a summary of the reporter used a heating method to observe the temperature difference of the pipe upstream and downstream, and used this to determine the direction of flow. To model the system, he used the finite element analysis and considered each volume element and used conservation laws to determine his theoretical predictions. He experimentally verified these temperature differences across various parameters using this finite element analysis, and he's optimized his setup to obtain a larger temperature difference by considering effects such as the time taken and the distance between the heating element and temperature sensor. I also believe there are some strengths and areas for improvement in the report. So for the strengths, it was discussed about how the Hall effect and acoustic methods have certain limitations, and how he ended up using the heating element method. And I believe it's quite commendable, as he's able to discuss why the heating element is preferred and has shown understanding of different methods. He also has an analytic solution for the partial differential equation of heat flow, and I believe that this increases physical insight, as we are directly able to see what parameters can be used, what parameters affect the temperature difference. He's also obtained a successful device to determine the direction of flow, as this is asked for in the problem statement, and he has been able to observe the temperature difference. He has also experimentally optimized many important parameters, such as the temperature of the heating element, the position of the measurement, as well as the time after the heating element is switched on. I believe this is quite commendable, as this relates to a large range of optimization and brings more physical insight into the problem. For the areas for improvement, I believe that the reporter has an unclear definition of the smallest possible flow, as he does not explain how his error bars in his graph are plotted, and since the temperature difference is inherently what determines the direction of flow, he should elaborate more on how these temperature differences relate to the noise, and hence we are able or unable to determine the direction of flow, and I'll discuss this more. The reporter also used a black box simulation with the fluid element mesh, as the equations he discussed are not used in this simulation. And I believe that this would invalidate some of his equations, as we see there is still differences between his analytic theory, and the black box simulation. And I believe he could have solved his own equations and compared these to the experimental plots. This would allow for more predictive power over the phenomena. There's also a poor qualitative explanation of the phenomena, as we are not able to fully understand the effect of relevant parameters, as a lot of plateaus and maximas in graph were not fully explained, and the reporter simply suggested that it's either increasing or decreasing with those parameters. Investigation of different fluids have also not been discussed, such as changing the heat capacity and conductivity, and these have not been experimentally verified. I believe this is quite significant, as a device should be able to work for all or many types of fluid. And this also relates to how the gas, since gas is also a fluid, we need to discuss how gas would be affected by this heating element. Because the problem statement does clarify that we need a non-invasive device, and using a fluid such as gas would cause the fluid to expand non-uniformly, and hence could be considered invasive. And I think this is a valid point, and a reporter should address this. And the reporter has also mentioned that the maximum temperature is limited by the phase transition of water. And this would mean that they have very limited scope for the experimental device. And this leads to and this means that the reporter probably should have investigated gases. There's also unclear experimental conditions and quantitative model, as the equations and assumptions used are not explained, and how these deviate from the black box sim in the finite element mesh. He also did not consider contact resistance.
Okay, time is up.
I'd like to now
Okay,
invite
it's
the
time to
reporter up.
start discussion.
So,
Right, thank you. Can I share my screen, please? Yeah, if you want to take a look at my slides.
yeah, thank you. So,
Right. Hang on for a second.
Good.
I'm getting the permission for sharing my screen. Oh, okay. Thank you very much. I get it now. All right.
So for some of your equations, you have error bars for the temperature, correct? Could I ask how these are derived?
Yeah, I can explain it to you. Like the error bar here, the upper, let me have my pen here. The upper one indicates the maximum result we have in our experiment, and the lowest bar represents the lowest thing we have in our temperature, and and it means the range. Okay, and for each bar we have to do 3 experiments.
So could I clarify whether you repeated this multiple times and then from there derived the error bars, or was it for a single run? And okay, thank you. So from these error bars, how do you determine whether or not you consider the direction of flow to be measurable or not?
Yes, okay. You mentioned that in our discussion part, and I'll explain it to you. And the minimum measurable, like the minimum temperature difference that our apparatus can measure is 0.05 Kelvin. Okay, so if the temperature difference drops below 0.1 Kelvin, and we have made a very conservative enlargement here, it would be considered insufficient. So as you can see, this one here, okay, it signifies 0.1 Kelvin. And this
the 0.1 is derived from your error bars, is that correct?
It's not derived from our error bar. It's derived from the accuracy of our temperature measurement system.
But however, I don't think this would be quite accurate because just because your temperature sensor is precise to 0.1 Kelvin, this doesn't mean that the noise predicted, which should be analogous to over different runs, how different your temperature sensor would be. And this would mean that if your minimum flow measurement might not be very accurate. Let's say if you were to compare hundreds of runs, half of them may be one direction, half may be the other direction due to the noise. So I believe a more
okay, I wanna correct you for your statement. The minimum accuracy of our apparatus for temperature measurement is 0.05 Kelvin. And then we have set our limit that we would consider to be insufficient higher than 0.05 Kelvin, which is a very conservative enlargement. Okay, so I think
I understand your point. I still think that this is not what fundamentally determines whether or not it's measurable. So I think a better way would be to consider many runs, and then from there, let's say 90% of the flows are able to be predicted accurately. So in the interest of time, and this is not a very significant point, so I'd like to move on. So I noticed that in your graph, intersection between the temperature and the actual flow is not at the origin. But one would expect that if there's no flow, then the temperature difference would be 0. Is that not right? Sorry,
yeah, you mentioned the graph. Which graph? Sorry,
the one you were at just now.
Oh, okay, fine. Okay, this one.
Yep, thank you.
Okay, what question did you ask? Sorry, like.
Why does it not intersect at the origin? Because at 0 temperature, would we expect zero? Sorry, at 0 actual flow, we would expect 0 temperature difference. Is that not right?
Sorry, I don't understand your question. Could you just paraphrase it?
Like the graphs intersect or the origin, correct? Because when there's no actual flow, then there's no temperature difference. So why is it that it intersects slightly away from the origin?
It's not linear. Yeah.
If it's not linear, then how is your simulation results show a linear trend? Because at the high actual flows, we also notice a plateau. So do you think that there could be another competing factor, such that if you increase actual flow by quite a bit, the temperature difference would actually decrease?
Well, sorry, I didn't quite actually understand your question. Do you mean that as this point goes towards the origin, the deviation would be smaller? Is that what you mean?
Yes. Essentially, why is it not at the origin?
Well, it doesn't matter whether it's not at the origin. At the flow of 0.3 cubic centimeters per second, or temperature difference 0.1.
Okay,
I don't see the reason why it's at the origin.
Okay, I'd like to move on. So we disagree on that, but I think something more significant would be if you consider a limiting case where the flow velocity is very, very high, then the temperature, the water passing through the heating element would not have sufficient time to gain heat, correct? So as it passes through the outer side of the pipe, it will not be able to conduct it away, and hence the temperature difference would not be very significant. But however, in your line there just now, it shows a linearly increasing trend. So I don't think that's very accurate.
Well, I think let me just take a look at put these slides of thermal conductivity here. Like I think your what you have mentioned is not quite correct. Yeah, take a look. We have tried fluids with different thermal conductivity. We didn't try fluids with different thermal capacity. The reason is that just listen to me. Okay, I'll explain your question. Okay. You mean that when the water is passing very quickly?
I don't think this is relevant. Could we go back to the velocity?
Sure. It's indeed that fluids will not have a very high increase in temperature, but thermal conductivity matters. It's not the thermal capacity matters. Okay, we don't care whether these.
I do understand, but I think you misunderstood my question. So, if we increase the same for the same fluid, if we go at let's say 0.1 meters per second versus 1 meter per second, the time it takes for the fluid to gain heat would be less. There will be less time for the faster fluid to gain heat. Is that not right? So when you go to so this will cause a decrease in the temperature.
It doesn't matter whether the fluid would gain heat or not. It matters whether the fluid would pass heat. Okay,
but if it's less
this
heat
is
to
my
gain,
point.
then there's less heat to release. Is that not true? If it's a lower temperature, there will be less heat transfer. If it doesn't gain as much heat, it could not release as much heat.
Yeah, sorry. It doesn't matter. The accuracy of this apparatus doesn't matter whether the fluid would gain heat or not. Then what matters is whether the fluid would transmit heat, which why we have thermal conductivity instead of thermal capacity here. Okay, this is my point.
But however, I don't think this is quite relevant. However, in the interest of time, I like to disagree because I think that the reporter is trying to show the thermal conductivity and capacity. However, I'm more talking about the fluid flow itself. So
yeah, okay. So I think we can move on. Right.
So
okay.
Could you go to slide 61?
Definitely. Slide 61. Okay, let me just go to very more fancy mode. 61. Yep.
So this is your how your thermal conductivity affects the minimum flow rate, right? So we notice in this graph also, there seems to be a plateau at the end where there's a very high thermal conductivity.
There seems to be a plateau.
So could I also ask, do you have any theoretical predictions for this? Because you have a simulation, correct? So you could vary the thermal conductivity.
What I have explained in that we don't really have much theory based on this one, but it's very easily to understand that as the thickness of that how can I say it's what do you mean that it's not linear? It has a plateau here.
Yes. So it's also why do you not have a theory on this? Don't you have a?
Sorry, it's my mistake. We have a theory on this indeed, but the plateau here in that
your
can just
finite element model. You have a theory for that?
Yeah, indeed. Sorry, I correct myself. We have a theory here, and the theory predicts that it's inverse, and it verifies this. The reason for this plateau is that we have a fitting curve here. Okay, it's not the theory result. And the theory can only predict that as thermal conductivity of the tube increases, the accuracy decreases, and it cannot predict the plateau. The plateau is resulted from our actual experiment.
Okay, okay, I understand your point. But I think you could have formed your own theory graph using your finite element method. This would be more physically insightful and wouldn't lead to the discussion we had. The misunderstanding we had, and also it reduces the predictive power of your
your
experiments. You could
sorry, which
use finite element method. Sorry. Could I ask so your maximum temperature measured is 310 Kelvin. Is that correct? Sorry, your maximum optimal temperature.
It's optimal temperature. Yeah.
Yeah,
optimal temperature of measurement.
So why doesn't it just increase indefinitely?
Yeah. If we increase it to 1000 Kelvin, the water would evaporate. Do we want to make the water evaporate when we are trying to measure the direction?
But the boiling point of water is 370, is that not right? So why not 360 or 50?
Well, the kind of fluid is not determined. Maybe we can use alcohol. The boiling point of alcohol is very much lower than that of water. Yeah, so this apparatus should be fit for measuring the direction of multiple fluids, not only for water.
Okay, I think this is why I think your method is actually invasive, as it would affect the phase change, and your accuracy is not fully determined by your.
Okay, I'm afraid we're going to have to stop there.
Thank you.
Okay, opponent, you now have 1 minute for concluding remarks.
So in summary of the report, the reporter and I have discussed his experimental error bars, and I think that the experimental error bar should be what is used to derive whether or not the temperature difference is significant and can be considered to and we can consider whether or not the direction of flow can be used. And I think the model the reporter used is quite insufficient as it only considers the precision or a scaling factor times the precision of the measurement. We've also discussed the we've also discussed how a very fast fluid would result in lower change in lower difference in temperature, and the reporter showed a linear trend. However, I believe that there are more factors to be considered and that this is not very accurate. We've also discussed why the heat capacity of the heat capacity of the fluid will cause an asymptote, and I believe that the reporter could have theoretically shown this with the simulation. With the finite element method simulation. We've also discussed why 310 Kelvin is the optimal temperature. However, due to the lack of experimental verification, I
Okay,
believe
time is up.
fully answered.
Okay. Gordon, you have 2 minutes.
Yeah, we're trying to share screens. First of all, thank you very much for the suggestions and the discussion points from the opponent. It's very valuable. And first of all, let's have a rewind on what we have discussed. The first one, it's a clear definition of minimum flow. Okay, at 310 Kelvin, we have a minimum flow of measurable of 0.3 cubic centimeters per second. And then how about using ANSYS simulation instead of our own simulations? It's because the ANSYS simulation engine follows the basic law of fluid dynamics and thermodynamics, such as the conservation of energy and mass, which are in agreement with our equation. So there's no evidence for our black box simulation. Okay, so how are these error bar calculations and how to make sure that they're measurable? Okay, we have performed 3 trials per data point, and the error bar indicates the ranges of our data. And does the cross-section of the water have the same temperature? It's a good point raised. No, but this does not affect the overall accuracy of the apparatus. And what if the flow does not have enough time to absorb heat? The core thing is, it doesn't matter whether the fluid would absorb heat or not. What matters is whether the fluid would transmit heat. Okay. So entering our next slide, we have several very worthwhile suggestions. Thank you, Team Singapore. First of all, we have to run multiple trials, and if 90% of them are accurate, then it is measurable. Okay, I do agree with that, and actually I can combine this one with the accuracy of our temperature measurement apparatus, and then we can find out what is the minimum flow measurable. And then I have to combine the finite element analysis with theory as well. So I now want to have a rewind on what I have done. I have performed theoretical analysis on the temperature field of my apparatus, and then we have done some experiments and simulations, and we find out in our later charts that these 3 things have a brilliant coupling with each other, which I think is the core of our experimental research and scientific research. Thank you very much. Thank you, Team Singapore. I appreciate your suggestions.
Thank you very much. Okay, could we please have all the jurors back on screen? Okay, here we go. Could you perhaps please leave your presentation on screen? It may be needed for questions and it may save time. Okay, can I just ask quickly first to the opponent, do you think that a fluid can transmit heat without first absorbing it?
No, I don't think so, because it will be proportional to the temperature difference if you're assuming it's conduction, that's the heat transfer form. So if there's a lower temperature difference, there'll be a lower temperature emission.
Thank you. Any other jurors? Alex.
Short question to the reporter. Did you change the direction of the flow?
Yes, we do change the direction of flow.
And every time you can say the direction and yes.
Okay, yes. Every time we change the direction, we will start up a completely new experiment to affect the influence on the previous experiments. Thank you.
Alan.
Just with the point that's been raised about invasive or non-invasive, do you feel, to the reporter, do you feel that heating the fluid does not change the fluid in any way? Is it
yes.
non-invasive?
Thank you very much for this question. I think our selected temperature of 310 Kelvin is not enough to change the phase of the fluid for common fluids. Yeah. So it's not considered as invasive, and it will not change the core thing, that is the direction of flow.
Claire, if we have time, I'll come back. Alan.
Okay. This is to the opponent. Given the temperature range by the reporter, do you think that the temperature change in fluid will change the flow rate of the fluid?
No, not for the range of temperature used and for water specifically. But I believe if you use a gas or a very high thermal expansion fluid, this would change the flow rate.
Gavin?
To the reporter, how long does it take to actually stabilize the temperature so that you can verify your measurements?
The peak of temperature happens at 0.5 minutes, and then after 0.5 minutes, it starts to stabilize and reach a constant temperature. Thank you.
So just a follow-up question then.
Okay,
so
sure.
if the flow was variable,
Yeah.
one way and then the other way, what would be the minimum time period that you could detect between the flow reversing?
Yeah, that's a good question. In our experiment, we have done these trials. It's about 1 to 2 minutes, depending on the actual velocity or the flux of the fluid.
Alan, I believe you had another question.
Yeah, thank you. The opponent raised slide 61, where you had a graph where you had 4 or 5 points with error bars, and only 2 of them seem to cross your trend line. Yeah, thank you. That's the one. Do you really feel that the idea of the plateau you're discussing is strongly supported?
It's not strongly supported. Actually, it's a fitting line of our experiment value to show a general trend, but it's not derived either from theory or from simulation. It's just a fitting curve to show the trend.
Can I please ask can I ask you to go to slide 54? Just a question about your experimental setup. Now this was, or somewhere around here, you did maybe the previous slide 53. You used different fluids. That you had a table of, I think, 53. And I'm assuming you had a flow rate meter in the system somewhere?
Yes.
Did that flow rate meter, I'm just wondering how that compared, how did that work with gas? You've got air as one of your fluids. How did you make sure that was the same working? How did you have a meter that measured liquids the same as gases?
Yes, we use different flow meters for fluids and for gases.
Okay, thank you. Gavin, did you have a quick question?
Yes, it was on the last graph, the previous one that Alan was talking about the thermal conductivity.
61, I think it was.
That's the one. So to the reporter, you said the thermal conductivity increases, the minimal measurement decreases. So if the thermal conductivity was very, very small, what effect would that have on your readings?
Let me think. If the thermal conductivity is very small, I think it generally feels like no fluid is moving. So actually, when the thermal conductivity is really small, we will not be able to measure the direction anymore. So actually, I think this conclusion should be based on the fact that the thermal conductivity is higher than one gap, than one thing. For example, we say like
Okay, that's fine.
one.
Thank you.
Okay, time is well up there. Okay, so we'll now decide on our grades and enter them into the system. Okay, apologies for the slight delay. We had a little technical issue there, but we're back now. Okay, so for some comments on the report, I'm going to ask Alexander, would you care to comment on your grade for the report?
Okay, I very highly appreciate this report, of course, because the phenomenon explanation is very good. I highly appreciate the number of the models which the reporter explained, and I very like the size communication, of course. But in my opinion, it was some maybe misunderstanding between the reporter and the opponent in the discussion. So the discussion could be quite better, maybe.
Okay, thank you. And we'll also ask Gavin for a comment on the report. Muted again, Gavin.
Okay, we're back. I could, congratulate you on the amount of time you've obviously spent on developing your method. I was not too sure about the sensitivity of some of the devices you were talking about, and the fact that it took such a long time to actually get readings, that the flow would have to be that long. I was perhaps hoping that you would have come up with another system. That said and done, the effect of the thermal capacity of the water, or the fluid, should I say, as well, in that discussion, I was not convinced.
Okay, and for some comments on the opponent, we're going to ask Alexander again for some comments for the opponent.
Yes, I would like to comment the opposition. So the question asked, in my opinion, were not too short. After that, the opposition speech, the time management, in this case was only fair, not good, and the opponent spent a lot of time for telling about the some issues in report, but he didn't express his own opinion. And the discussion with the reporter was rather chaotic, in my opinion, and sometimes irrelevant.
And Alan, ask you for a comment.
Yeah, I'm probably different from the last comment. I found the report itself had certain issues, and the opponent raised the ones I was looking at. They raised the idea of the invasive or non-invasive. Given the temperature range they said, I'm still not convinced that that is a non-invasive procedure, and that was made very well by the opponent. They also talked about the issues with the various experiments and whether the data fitted the actual trends that were being shown, and I thought that was in agreement. So I felt they raised the issues I was concerned with, and they got it explained to a higher degree.
Okay, thank you very much, everybody. That brings us to the end of stage 2 of the finals. We have one stage remaining, with which the third stage will be the team of Singapore reporting problem number 14, ball on a membrane, and they will be opposed by the team from Canada. It is now just about 8:30 on my clock here, so I will suggest we have a 15-minute break. Be ready to back to start at whatever it is, 45, but 8:45 where I am, or 45, whatever it is for you. So 15 minutes. Thank you very much, everybody. Okay, just checking, do we have, I think we've got all of our jurors here. Do we have the team from Canada? The team from Canada here, could you turn on your camera, please, so we can see the. Here we go. Excellent. Cool. Okay, so I believe we have everyone here. We've got in the last round the team from Singapore presenting problem number 14, ball on a membrane, being opposed by the team from Canada. So we'll get underway. And before we start that, just one announcement. At the conclusion of this stage, if everyone just wants to stay here in this meeting, we'll just have a brief few minutes just to sort out the scores, and then we'll do the sort of closing ceremony straight at the end of this fight, to just a few minutes. Okay, so just stay here at the end if you want to find out what happened. Okay, so we have Singapore reporting, so you now have 5 minutes preparation time.
Could I check if you're able to see my slides?
Yes, we can.
All right, thank you. Oh my God. Sorry. Then could I start now?
If you're ready to start, can I just check the team from Canada? You're all ready? Yep, I think we're okay. They're there. Absolutely. Okay, so you can start your presentation now.
Okay. Hello everyone, I'm Akshat Vijay, and today I'll be presenting problem number 14, ball on membrane. The problem statement tasks us with investigating the sound produced when a metal ball is dropped on a rubber membrane stretched over a plastic cup. We're asked to explain its origin and how its characteristics, such as the pitch or frequency and the amplitude, depend on relevant parameters, such as the impact conditions, the membrane properties, as well as the length of the cup. Here's my content outline for today. I'll first be covering some preliminary observations, followed by the dynamics, acoustics, experimental verification, and further insights. I'll first start with the preliminaries. This is my experiment setup. A hollow plastic cylinder was used as a plastic cup, and latex sheet was used for the rubber membrane. An electromagnet was used to release the ball. A condenser microphone was used to record the sound produced, and acoustic foam was used to filter out any background noise. The release mechanism consists of an electromagnet mounted on a moving stage in order to precisely adjust the height and position of release. Here's a video of the electromagnet. It ensures that there is no initial velocity and that there is consistency in the release of the ball. By performing an FFT on the sound recorded, we can see that there are multiple key frequencies detected. Additionally, we contrasted the sound produced without a cup with the sound produced with a cup. It is clear that the presence of a cup has a clear effect on the sound produced. By performing an FFT of the two sounds, we can see that there is a deviation in the location of the peak frequencies. We will discuss this later. But first, let us cover the dynamics of the system. I'll first be qualitatively explaining the ball's motion. Initially, the ball falls down and collides with the membrane. This compresses the membrane, indenting it downwards. Due to the stored elastic potential energy, the membrane moves up and releases the ball. Hence, we realize that in order for multiple bounces to occur, the collision between the ball and the membrane must be as elastic as possible, while the compression of the membrane must be as high as possible. This explains the choice of a metal ball and a rubber membrane in the problem statement. It is important to note that throughout the depression and rising of the membrane, the ball is always in contact with the membrane, and hence the membrane cannot vibrate, so no sound is produced in this stage. Using edge detection techniques, we're able to parameterize the curvature of the membrane when a force is exerted on it. By fitting this to the force displacement equation of the membrane, we are able to determine the tension in the membrane. We may analyze the forces acting on the ball, and by considering the depression height h at a given instant in time, we can write the normal force acting on the ball as a function in H. We can then express the potential energy of the membrane ball system as a sum of the potential energy in the non-contact region of the membrane, the energy due to the stretching of the area in contact with the ball, and the loss of GPE of the ball. Here, W is the contact radius. We now take the derivative of the potential energy with respect to the contact radius and equate it to 0 in order to determine the maximum depression height of the membrane H max, which will be needed to model the acoustics. Next, I'll be covering the acoustics of the system. Once the ball is released from the membrane is displaced above its equilibrium position, causing it to oscillate. Hence, it vibrates at certain frequencies, producing transversal waves on the surface, which we're able to hear, similar to musical drums. In addition, the internal air and the external air can assist in modifying the sound heard, and this will be further discussed. Now, let us continue from the dynamics of the system when the ball causes the membrane to deflect downwards. In the absence of the ball, the membrane oscillates naturally, following a two-dimensional wave equation. But once the ball strikes the membrane's displacement can be modeled using the force displacement equation, as covered previously in the dynamics section. In order to analyze what happens once the ball leaves the membrane, we will consider the vibrations that occur along the surface of the membrane. We model the membrane using thin plate theory, allowing us to obtain this wave equation. This allows us to obtain a general solution for the displacement of the membrane. Here, Jm is the Bessel function of the mth order. As a result, we're able to predict the various modes of oscillation in the membrane. Analyzing the membrane from the top view, we're able to impose the following initial and boundary conditions on the system. As a result, we're able to obtain an analytic expression for the peak frequencies, as well as their corresponding displacements. Looking at the expression for the displacement, we can see that there are two terms that are time independent. Let us analyze these more closely. Equating the first term to 0, we obtain a sequence of radii which remain at rest throughout. These are the circular nodes, which are represented by M. We also obtain a sequence of angular positions, which are the diametric nodes. These are represented by N. In order to evaluate the overall membrane displacement over time, we may superimpose the various activated modes. Here, we can see how mode 01 and mode 02 superimpose to form the overall membrane motion. In order to experimentally verify the existence of such modes, a loudspeaker was used to vibrate the membrane at certain frequencies, upon which light particles had been scattered. It was observed that only at certain peak frequencies, resonance of the membrane caused increased vibratory motion, driving the particles to the displacement nodes on the membrane. Experimentally, we can clearly observe these modes from the equilibrium position of particles at the stationary points on the membrane, which are the nodal lines of each oscillation. Now we're able to predict the peak frequencies. Comparing our theoretical predictions with the experimental data for the sound produced without a cup, we can see that we have good predictive power over the peak frequencies. However, these same predictive frequencies, when compared to the sound produced in the presence of a cup, seem to deviate significantly from experimental data. Hence, in order to reconcile our theory with experimental data, we will consider the concept of air loading. Consider the membrane cup interaction. Zooming in, we can see that initially, the membrane is pushed inwards, which causes the internal air to be compressed. This results in a pressure difference being created in between the external air and the internal air cavity, effectively coupling the membrane to the air. This pressure difference results in a net upward force exerted on the membrane, which increases the restoring force acting on it. As a result, the peak frequencies of the system are higher than expected, and we have to account for this. In addition, for a membrane without a cup, we notice that the amplitude of the sound is significantly lower than that with a cup. This is because when a membrane vibrates freely, the sound wave rarefactions produced above and below the membrane are out of phase, destructively interfering with each other. However, when a cup is used, this destructive interference is removed, hence increasing the sound amplitude received. It is important to note that the deviation we observe experimentally is not due to the presence of standing waves resonating in the cup. We can see this by comparing the frequency versus length of cup for the experimental data and for theoretical standing waves. We will be returning to how the length of the cup actually affects the frequency later on. In order to account for the coupling between the membrane and the air, we first define the set of cylindrical coordinates and take L to be the length of the cup. We now modify the wave equation, adding on the terms for the internal and external pressures as well as viscoelastic damping. We may assume harmonic time dependence since the membrane still exhibits harmonic motion to produce these frequencies. We then impose the following boundary conditions, such that there is no change in pressure outside the vertical column directly above the membrane, and there are no vibrations at the edges of the cup, as we assume the walls to be rigid. Writing the internal and external pressures as such in terms of the Green's function, we then express the displacement of the air-loaded membrane as a function of an eigenvector multiplied by its displacement in a vacuum. Now, using a numerical eigenvalue eigenvector system, we're able to solve for solutions for omega and phi that correspond to each mode of oscillation in the membrane. Next, by considering the coordinates of the impact point, we obtain an equation for the initial acceleration provided by the ball. Here, W is once again the contact radius. Now, by considering the initial acceleration effect and substituting in the given eigenmodes, we can solve for the relative amplitudes. By coding an eigensystem simulation, we were able to obtain a time-dependent pressure distribution graph, which superimposes the individual sine waves. By performing a discrete Fourier transform on the pressure distribution graph, we obtain the locations of the theoretical peak frequencies. This allows us to compare our theory with our experiments. Now, moving on to the experiments. Returning to the graph of the sound produced with a cup, you can see that our new theory, which accounts for air loading, has good predictive power over the peak frequencies. We vary the tension in the membrane by drawing concentric circles on the membrane and stretching it over a cup, which ensures equal stretching. From our experiments and theory, we can see that increasing the tension would increase the frequency of vibration, as it would increase the stiffness of the membrane, which increases the restoring force acting on the membrane. By varying the height of release of the ball, we observe a consistency in mode activation, but varying amplitudes were observed for each mode for different heights of release. We note that increasing the height of drop increases the amplitude of the frequency, and this is because when the ball is dropped higher, the initial deflection would increase, amplifying the vibration of the membrane. By varying the diameter of the ball, we see a similar trend to varying the height of release, with the location of activated modes being consistent but varying in amplitude. This can be explained by considering that when the diameter of the ball increases, the contact area with the membrane increases as well, which reduces the activation of circular modes. At the same time, we see that there is a higher activation of diametric modes, and this is once again due to the increase in the contact area between the ball and the membrane. We also vary the length of the cup by using a 1 meter glass cylinder and filling it up with water. A floating disc was introduced to prevent vibration effects of the water. Comparing our experimental data with theory, we can see that increasing the length of the cup reduces the internal pressure generated by the deformation of the membrane, hence decreasing the effective stiffness of the membrane. As a result, the restoring force of the membrane decreases. We see that all three curves converge towards a horizontal asymptote, which is simply the limiting case of our air loading theory with infinite air volume. This is the case without a cup, and we can predict this by thin plate theory. Next, we vary the impact position of the ball. We can see that the modes activated are different in this case. This is because varying the impact position changes the initial acceleration experienced by the membrane, affecting the relative amplitudes of the various eigenmodes. We were also able to quantitatively predict this change of frequencies and corresponding amplitudes for different impact positions, once again seeing good agreement between theory and experiment. Now I'll be moving on to some further insights. For our experiment, we would take a FFT of the overall duration of a single bounce, but by taking a FFT of a small moving time frame on a single bounce, we interestingly noticed that mode 2.2 would decrease in amplitude extremely fast, but mode 5.2 would decrease in amplitude less rapidly. We can aim to explain this by considering that as the number of diametric nodes that a mode has increases, the more radially asymmetric it becomes. As a result, 5.2 would have 5 sectors of the membrane undergoing rarefactions, while the other 5 undergo compressions at the same time. Hence, the radiation of sound is less powerful for modes with more diametric nodes, but as a result, they attenuate much slower. In addition, by performing an FFT of the sound produced at the start compared to the sound when the ball's bouncing is about to terminate, we see that a new higher frequency originates towards the end, which took the form of a chirping sound experimentally. We can see that the ball bounces on the membrane from a closer height over time. Hence, this collision frequency increases. Initially, this collision frequency is very insignificant, as by the time the ball falls back down and hits the membrane has already stopped vibrating. However, as this frequency increases, the ball strikes the membrane at around the same rate that the membrane itself is vibrating, so period coupling occurs. This results in a new frequency being detected. Now I'll be providing a summary of the report. I qualitatively explain the sources of sound and their dependence on relevant parameters while explaining the role of air in the deviation from thin plate theory. I was quantitatively able to model the fundamental frequencies and amplitudes both in the absence and presence of air loading, as well as the dynamics of the system. For my experimental account, I verified my theory for various parameters while qualitatively investigating frequency evolution over time, as well as termination effects. Here are my references. Thank you for listening to my presentation.
Thank you very much. Okay, the opponent from Canada, you now have 2 minutes to ask clarification questions.
Okay, thank you. First, I would like to thank you for this great presentation. So I just have some clarification questions to ask you about. First, what are your frequency error in your measurement? or the main frequency error? Answering concisely, thank you.
So you're asking like what causes the error in the frequency, is it?
Yes, in your
Usually it would
measurement.
be, yeah, usually it would be the fact that the place where we actually drop the ball on is not actually at the center. So it's a bit to the right or a bit to the left.
You have about 20 seconds. Be ready to start.
Okay, I'm ready to start.
Okay.
So, okay. Hello, everyone. I'm Jeff Lee from Team Canada, and I'm here to oppose problem 15 ball on membrane. And the problem statement reads below: when dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. And want to explain this origin of the sound and explore how its characteristics depend on relevant parameter. Some tasks that we think that the reporter should do are: first, they qualitatively explain the origin of the sound in the phenomenon which they partially explain. And also, second task is to construct a repeatable experimental setup that controls membrane and ball properties, which I also think they partially fulfill this requirement, and we'll discuss later. And also, the third test is they theoretically characterize the motion of the membrane and predict the sound created. I think they also partially fulfill this requirement. And fourth one is that they need to experimentally verify the effect of relevant key parameters. I think they fulfill this part. And the summary of the report: first, they went over their dynamics of the phenomenon. They qualitatively explain the vertical deflection of the membrane and the balls collide with the membrane. Also, a force analysis and energy calculation of the ball on the membrane. And then they move on to their acoustics part of their presentation. They first talked about the modes of vibration and also Bezier function, and also they talk about the Chladni patterns to show the pressure and also the sound pressure, and also various parameters on their plot. And they also talked about the air membrane coupling, and with a scenario that the membrane has a cup below it. And then they move on to their parameter analysis, and they vary different height, radius, and length, and they compare the experimental data with theoretical model. Some merits that we think that the report actually have, like, they have a very good dynamics calculation, they have a good energy consideration of the phenomenon, and they actually have a good theoretical model. They consider the air membrane interaction and also the thin plate theory, and also they have a Chladni pattern visualization that they use small particles to visualize the vibration models. And some possible next step that we think the reports can be improved on: first, they have an unsatisfactory qualitative explanation of where does the sound come from, and also the natural frequency of the vibrating object and the microphone. Second, they have insufficient quantitative models, like their error is not analyzed, and also the stability analysis of the ball bouncing on the membrane is not discussed, and they use the single bounce instead of multiple bounce model to analyze this problem. And third, they also have some experimental issues that they didn't fulfill. They lack the change of geometry, which is like they only use circular membrane instead of membranes in other shapes. That it's very related to this problem. And the problem actually said a membrane, but didn't mention what shape it is. And that's a parameter, important parameters to vary. And also they have a lack of verification of the uniform tension of the membrane, and they also lack of investigation into the damping motion of the membrane. And the multiple bounces is not considered in their measurement and in their experimental data, and also the theoretical model. So some discussion that in the discussion, we will talk about some qualitative explanation of the origin of the sound. Second, we will talk about some possible improvement that can improve the experimental setup. And also, we can discuss about multiple bounces versus single bounce, which is the point that they didn't talk about in their report. And also, we can talk about and discuss about the chaotic nature of the phenomenon and how that actually influences their result and potential influence it will have on their phenomenon. So here I will move on. I would like to invite my the reporter for a fruitful discussion.
Sure. Could I ask for screen sharing access?
Sure. So while you're doing the screen share process, I actually have several questions to ask you about. So the first thing, we want the qualitative explanation of the original sound. What do you think are actually vibrating in the phenomenon? And what do you think are actually creating the sound? Can you list them out, like in one sentence?
Sure. Okay. So the origin of the sound is due to the fact that when the ball hits the membrane, it actually compresses the membrane a bit, And then because the membrane is elastic, it'll move
Yeah.
down a bit, and then due to this energy, the elastic potential energy, it will then release the ball. And do you agree with me on that?
Yes, I actually agree with you on that, but I was wondering what object was vibrating and creating a sound? Can you just list them out?
So it's the membrane that's vibrating, because once it's been displaced from its
Okay.
equilibrium position.
Okay, I understand. Did you consider the ball vibration, the cup vibration, and also the air inside air surrounding the membrane vibration? Did you put that into?
Yes.
And also
yes. So sorry, let me just clarify something.
Sure.
So the
Okay.
vibration of the air is the whole essence behind the air, the air loading theory. And what we're saying here is that when the membrane is pushed inwards due to the deformation caused by the ball.
Sorry to interrupt.
Sorry. Could I just finish my point first? Sorry. Then this will actually cause the internal air to be compressed, and as I've explained, the pressurization is the thing that causes the deviation.
Okay. Yes, I understand this question, but actually the sources of sound are different. Like the cup, did you verify and measure the natural frequency of the cup, the microphone? Did you do that?
We actually did.
Okay.
What we did is we compared the sound produced when the cup was clamped versus when it was unclamped, and you can see that there is very limited deviation, meaning that the walls of the container are rigid, and this is an assumption that we have.
Okay, then I think we can move on. Okay. So
Sure.
About the experimental improvement, I remember I mentioned earlier that you didn't verify that your membrane has a uniform surface tension, uniform tension along the membrane. Do you agree?
Yes, you mentioned this, but I do not really agree with your point, because what we've done here is that we obtain an equation from literature that allows us to characterize this tension, and this only works under the assumption that the tension is uniform all across the membrane. And as you can see, we observed a very, very good agreement between our theory, between the fitted graph as well as the experimental points.
Yes, but the rubber, like the membrane is made of rubber. So if it's rubber, that means the Young modulus of the rubber is non-uniform. It's non-linear. That means the tension itself is actually not uniform as the strain changes. So
I disagree with you regarding that, because what we did is we actually found the Young's modulus of the membrane by considering how the ball deforms it, by considering the mass of the ball as well as the initial and final lengths. And for the range of deformations that we're working with, because the oscillation is quite small, the Young's modulus is actually constant.
Okay. Then just have a very quick question, like what percentage of the to what percentage do you think the membrane actually deforms, like its length? Just tell me a percentage.
I would say that the deformation, because it does not occur like at the edge itself, is probably around 10% at most. Yeah.
10% at most. But the Young modulus.
10% of the thickness, as in, like, did you understand my point?
Then what about the length? Like, yeah, I actually agree with that on the thickness, but what about on the length of the membrane?
What do you mean
like
by
the radial
length?
length of the membrane?
Oh, the radial length of the membrane, it will only change by a very small portion. I can't exactly give a percentage, but the change is quite small, and so the Young's modulus is actually relatively constant.
Okay, so I think I actually agree with you on that. So I guess we'll just move on. And I actually have a suggestion on that to verify that there's a uniform tension. You can measure the thickness of the membrane, and then that would tell there will be a uniform tension if the thickness are nearly constant. Okay, so now we can move on to.
Could I just clarify? What do you mean by the stiffness of the membrane?
It's like if you measure the membrane, like if you measure the thickness of the membrane at different points of the along the membrane, then if you find a nearly constant membrane thickness, that means like it has a good agreement on the uniform tension. Okay,
that's a valid point. Thank you.
Okay, thank you. And also now let's move on to the now move on to our like the next question. So what do you think, like, if you're considering a model with multiple bounces, like in your question, I observed that you only investigate into one bounce for the ball. Do you agree with that?
Experimentally, we only considered one bounce. That's correct.
Okay, so what if we look into multiple bounces, because that's actually one part of the problem statement, that we want to investigate how ball bounces on the membrane, and that creates different sounds. So actually multiple bounces, I think, is a very important factor in the problem that you should actually investigate into. So let's say we are doing a experiment with multiple bounces of the ball on the membrane. So what do you think the sound change for every bounce?
So just to clarify, what you mean is that we're considering how the ball like bouncing on the membrane over time would affect the frequencies that are being detected. Is that correct?
Affect the frequency and the intensity, yes.
Yeah, so what you can consider is that when the ball bounces on the membrane, it will then be released to a rebounding height, which will be lower than the initial height. So let's say like this height is like some small h compared to the initial big H. And as I've shown here from my graph regarding the FFT for varying heights of release, we can see that the frequencies actually don't change. The only thing that changes is the amplitude of these modes. So what this means is that we essentially have a theoretical model that can predict how the amplitude would decay over time as the ball bounces like over multiple times. Does that make sense?
Okay, yes, I agree with you on that. And also, just one point that I don't like, I quite disagree with you, partially disagree with you on that, is that the frequency of the motion actually changed. Do you think that the damping motions, the frequency of the damping motion decreases? Do you agree on that?
Frequency of what motion? Sorry?
Of a damping motion, like a damping oscillation.
I'm not quite sure what you mean by the damping oscillations.
Like the membrane actually decreases in amplitude and also decreases in the frequency, because it's transferring the energy to the air surrounding it, and that actually resists the motion of the membrane. Do you agree on that?
Yeah, so when even if we don't consider like the case where the viscoelastic damping occurs, there would still be a loss of energy in the case with a cup, because the air inside is being pressurized. So there will still be a loss of energy, and this can also be theoretically modeled.
Okay, then for damping motion, the frequency decreases along with time. Do you agree on that?
Okay, as you can see from like over here, you can see for like when we consider like multiple bounces, like when we consider like the FFT for like a bounce that is happening much later in time, you can see that for the first mode here, the difference is actually not very significant. And instead, what we observe is that this new frequency arises. So if you're referring to the damping oscillations, I'm pretty sure that they do not actually affect the frequency in any significant way whatsoever.
Okay, I'd like to disagree on that, but we can move on. So I want a little bit clarification on this graph. By time equals to 37, do you mean like the multiple bounce of the ball stops at 37 seconds?
It's about to stop at around 37 seconds, correct?
But I'm just wondering, like, how do you know that it's actually the end of the bouncing, or that's not a coincidence of that it's just suddenly stopped because of any kind of coincidence? Because this phenomenon itself is it's very chaotic, because the membrane itself is vibrating while the ball itself is also moving up and down. So you can think like there are very strongly coupled oscillators in this phenomenon, that sometimes the ball, when they drop, it might be in phase with the membrane. The membrane is also intended downwards, and then they actually bounce out again with a higher intensity. And sometimes they're out of phase, that the ball membrane and the ball actually just collide with each other, and that actually causes a very chaotic nature of this phenomenon. So I'm just wondering, how do you actually make sure that t equals to 37 seconds is actually the termination of the phenomenon?
Yes, I agree, but we don't exactly have a theoretical model for this. And if you're asking how we're able to know whether the ball has actually stopped vibrating, well, we recorded a video of it, and what we would do is we would only take the FFT of the time frame that is around the time when we can clearly observe that the ball is only moving laterally on the surface of the membrane and not actually like bouncing up and down. So I do acknowledge that the motion is chaotic, and this is essentially a fact of this situation, but this does not really have much relevance to the sound created, right?
It actually has a very good relevance to the sound created, because the intensity, also the frequency, as their damping motion occurs, is actually decreased. So I think that's also one of the problem statements.
Time is up.
Okay. Thank you.
Okay, opponent, you have 1 minute for concluding remarks.
Okay, so in the discussion, we qualitatively discussed about the origin of and the vibration of the cup. And also, we then talk about how you can actually experimentally verify there's a uniform tension along the membrane, circular membrane that they used in that report used in the experiment, and how you can verify the Young modules of this thing. The report says that the Young modules is keep constant in the phenomenon, but I partially disagree on that. And we also talk about how much does the membrane deform and in what percentage. And we agree that there's very little amount of deformation, and there's a very little amount of deformation. And then we move on to talk about the multiple bounces that is relevant to this problem. And we talk about how the amplitude of the mode increases and decreases, and how the frequency is influenced by this motion. And eventually talk about the chaos and also the couple oscillations of this problem, which is a part of the problem statement. So thank you.
Okay, reporter, you now have 2 minutes for concluding remarks.
Okay, so as a summary of the discussion, the opponent raised up some points regarding the error in the frequency. And as I mentioned, this arises from the fact that the ball wouldn't land exactly at the center, and any small perturbation in the impact position might slightly change the frequency. However, this is quite insignificant. They also asked how we verified that there was a uniform tension. And as we mentioned, that the different tensions would not fit with the tension characterization graph that we have used. And we also use concentric circles and axes to make sure that they stretch equally. They also asked regarding how the non-uniform tension leads to shifted modes. And as I said, the non-uniform tension would lead to a ball changing position, which would cause the frequency to change over time. We also discussed a qualitative explanation of the sound origin. And as I've mentioned in the report, this is due to the vibration of the membrane after the ball has been released off of it. They also raised up a point regarding cup geometry. However, I believe that this is not a significant parameter to vary, because in essence, it is not the length of the cup that affects the frequency, it is rather the volume. Next, we also discussed the sources of sound, and as I've mentioned, we verified that shell vibrations and ball vibrations are negligible. Then we discussed how the frequency evolution would occur across multiple bounces. And as I've said, the frequency would not change with time as long as the ball keeps bouncing at the same location. While I do concede that the motion of the ball is chaotic, I don't believe that this has any much relevance to the problem statement, because we don't exactly need to predict how the motion of the ball would change over time. We also discussed the effect of damping of the membrane on the frequency. As I said, the frequency itself would not be affected much by the damping. It'd rather be the amplitude. And as I said, we have a theoretical model that can predict this accurately. So now I'll be providing a summary of the report. So I'll qualitatively explain the sources of sound and their dependence on relevant parameters, while explaining the role of air in the deviation from thin plate theory. I was quantitatively able to model the fundamental frequencies and amplitudes, both in the absence and presence of air loading, as well as the dynamics of the system. For my experimental account, I verified my theory for various parameters while qualitatively investigating the frequency evolution over time and termination effects. Hence, I believe that I have more than sufficiently answered the problem statement. Thank you.
Okay, thank you very much. Okay, can we now have all the jurors back in place? And can I please ask if you leave your presentation up? It may be useful for discussion. And can I just ask quickly, can you please go to slide 8?
Slide 8.
Now, can I just ask, how did you actually connect the membrane onto the cup?
So what we did is we basically placed we stretched the membrane on top of the cup, and then we placed rubber bands around the edges of the cup in order to ensure that the membrane does not slip.
Okay, in that case, how did you measure the tension? Like, from what I saw from your measurement technique, you needed to be able to see the curve. And if it's curving down into the cup, how could you see the curve?
So what we do is that we actually we characterize the tension after we've done the experiment, because as I said, the tension would remain constant as long as we use the same concentric circles. So then what we did is, after the experiment, we would flip the cup upside down and place a ball inside, and then characterize it using this equation.
So does that mean the bottom of the cup was open?
The bottom of the cup is, yeah, correct.
Is that a very good cup? I mean, I wouldn't want to drink coffee out of that. But
the bottom of the cup is not open in our experiments. I'm referring to the characterization. Like this, it's like
okay.
the cup is closed end. Yeah.
So I suppose what I'm asking is, did you measure the tension without removing the membrane from the cup?
Yes, we did.
Okay, thank you. Any other jurors? Alexander.
Question to the reporter: am I right that that the cup doesn't act as a resonator?
Yes, it does not act as a resonator. So if you're referring to the internal air cavity within the cup, so what we've actually shown is that the standing waves would not actually like agree with the experimental data that we have seen for frequency versus length.
And shortly, please, what is the role of the cup in this case?
So the role of the cup is simply for the pressurization of the air inside, which causes a deviation in the frequency.
So only pressurization of the air inside, yeah?
Yes, the pressurization of the air changes the frequency. Yep.
And a question about slide number 63. Yes. Please explain again what is time 37 seconds for the blue curve.
So this time equals 37 seconds was just we just took the FFT of the sound as the ball was basically about to stop bouncing, as we could see from the video.
Okay, it's a time of stopping bouncing of the ball.
Yes, it's around the
Can I just ask? It's related to this then. So this is the same test measured at the start and towards the end.
That is correct.
So is the sound at the end louder? Because looking at this, the peak is almost double the height.
Yes, that is correct. This is due to the effect of period coupling, and it happens when the ball is bouncing very, very fast towards the end.
Okay. Any other jurors ask questions?
Yeah.
Gavin.
Quick question for the reporter. You said that the membrane couldn't vibrate when it was in contact with the ball. Why is that?
Oh, that is because if we look at our qualitative explanation for the motion of the ball on the membrane, because the membrane is elastic, it actually will fall, like the ball will actually fall down with the membrane as it is compressed inwards. And because of this, like the weight that is exerted by the ball on the membrane, there's no avenue for the membrane to actually vibrate. So sound cannot be emitted in this due to the contact.
You don't think that a wave could spread outwards from the point of contact to the surface of the cup where you've got it clamped and back again?
That only occurs once the ball has left the membrane, because you need the ball to leave the membrane so that the membrane is actually able to freely oscillate. Because there's like a no slip condition being satisfied as long as the ball is in contact with the membrane, the ball will just continue moving with the membrane. So you won't have any vibrations occurring at that point. And what any initial wave that's caused by the contact of the ball will be rapidly damped out because the ball is still in contact.
Okay, a couple of quick follow-up questions then as well.
Sorry, Alan has a question.
Yeah, Alan, sorry.
Yeah, it's a follow-up question as well. On slide 63 that we're looking at, you were talking about 37 seconds and t equals 0, but you also said it was about multiple bounces, not one.
Sorry, could I clarify what you mean by that?
You said that the sound was created by multiple bounces, not a single bounce. How did you get the time? Hello?
Sorry, Shana, you seem to be muted there.
Sorry, I apologize for being muted. Could you clarify your question just now?
Just when you stated on 63, when you were presenting it, you said this was multiple bounces, not one, but there are at precise times. Can you explain that?
Yeah, so like it's at around 37 seconds. We were just taking it at a particular instant in time where we stopped the video and we recorded the FFT for a very, very short time sample. Yeah. So yes, many bounces are occurring, but it's for a very, very short time frame.
And what was that time frame?
Around 0.1 seconds.
Okay, we need to move on there. We will now move on to deciding on our grades. Okay. Thanks everyone. Okay, so for some feedback, we'll start for the report. Could I please ask Yongui for a comment on the report?
Yeah, I think their analysis is detailed enough, and their presentation was pretty nice. The discussion part went smooth, although not everything was resolved. So that's my comment.
Okay, thank you. And can we also hear for the reporter from Claire, please? You're still muted at the moment.
Oh, sorry. Yeah, I'm pretty much go along with the youngest comment too. You know, they did a very detailed experiment, but the problem statement asked about the original sound, but you know their explanation of the original sound is kind of in short. So and wasn't that much of interesting enough to lead the discussion. So that was my point.
Okay, thank you. And for the opponent, can I please ask Gavin to make a comment?
Okay. The initial questions, to be honest, I didn't think we found out too much there. And, at the end of the actual opposition, I didn't think we'd found out enough about the experiment. A lot of questions were asked, and many of them were answered fully by the reporter. But I didn't get a clarification from the opponent as to whether that was satisfactory and they agreed with them or not. And I did think that at the start, to be honest, some of the criticisms of the report were unwarranted.
Okay, thank you. And finally, for the comment on the opponent from also in the opposition from Alexander, please.
Yes, from my side, I appreciate the opposition speech because in this case it was well prioritized, and I saw a lot of own opinions presented by the opponent, and I like the discussion because all the points that I wanted to hear were presented.
Okay, thank you very much. So that brings us to the end of the competition part of the tournament. We're just going to take a few minutes now to let Felix have a pull through the scores and check a few things, and then we'll come back and we'll find out what we're all waiting to find out. So just hang on for a few minutes. We'll be with you soon.
Hi. Kent? I'm good.
Hello. Hi. Are you all good to go, Felix?
Yes.
Cool. Okay. So, everyone, this is Felix. If you haven't caught up with him before, he's the one that makes us all work. So I think we've got our 3 teams here. So I'll hand over to you, Felix, to do the announcing.
Okay. Thanks so much to all the teams for participating and making this whole thing happen. Congratulations to the teams who made it to the final, and I hope the other team members will also be here of the non-finalist teams, as we will have the whole closing ceremony with all teams, of course. So the non-finalist teams are also very welcome to turn on their camera and say hello, if there are any. Nice. Well, then we will start with Team Australia with 119.2 points. Congratulations to them. Then with 135 points, it is Russia. Congratulations. With 142.2 points, it is Thailand. Congratulations to Thailand. Further, with 157 points, it is New Zealand. Congratulations to New Zealand. And we had the rule from last year that up to the top half of teams get a bronze medal. So Korea with 161.5 points gets a bronze medal on 4th place. Sorry. Congratulations to Korea. Unfortunately, there is only one 4th place, one bronze medal. And we come to the finalists. And now it's even interesting to you because you haven't seen the grades. So with 35.7 points and a silver medal, it's Team Canada. Congratulations for an amazing performance in the final. Then on 2nd place, it's Singapore with 36.3 points and a silver medal. Congratulations. And 1st place with 37.0 points and a gold medal, Team China. Congratulations. It was a very tight, close call at the end with only 0.7 of a difference. So congratulations to all the teams of the tournament. I hope you enjoyed it. I will be mailing out PDF certificates in the upcoming week. Give me a bit of slack there. And I really hope to see the teams next year in person, but maybe there will be even more problems, and we now know how to do this, but all the social aspect is missing. So thank you very much, and I'll hand it back to Kent.
Thank you, Felix.
Yeah, thank you, Felix. Yes, congratulations to China, but congratulations to everybody. Yeah, just sort of to wrap up, I just want to say a huge thanks to everyone who helped make this happen. To all of the people who've worked behind the scenes, the flight assistants who've stayed up till quite early in the morning here in New Zealand to make this happen. The jurors from all over the world who've stayed up late or gotten up early, given up their weekend to help watch all these fights and help judge them. Thank you very much to all of you. To all the team leaders who had put in hours and hours and hours over the last year, really working on these problems. But most of all, to all of the students who've participated. I think back to what I was doing when I was a teenager, and yeah, you guys, I don't know what I was doing with my life, but I wasn't working as hard as you are. So yeah, congratulations to all of you. Just participating in something like this is yeah, a big amount of work, and so congratulations to everyone. Particular congratulations to our finalists today, and especially congratulations to the Chinese team for taking out the whole thing. But well done to everybody. Round of applause for everyone. I'm sure the scores will be up available online if you want to see what scores were actually awarded during the final. They'll be up shortly, I expect, for Felix. And I've said this several times already, but yeah, immense thanks to Felix for all the work behind the scenes. And yeah, we'll let him have a week to sleep and everything, so he'll get certificates out eventually, but we won't pressure him on that. Thank you very much to everyone, and I hope you have a great rest of your day or your evening or your morning. And yeah, hopefully we'll be able to see you all again in person next year, or if not, we'll have some way of we have a way of competing even if we can't make it in person.
And
thanks
you,
very much,
Kent.
everybody.
So well done to all the teams, and keep working hard. Spread the word about IYPT, whether it's at the physical or some other competition. Make sure people participate.
Goodbye, everybody. Have a good time.
Bye, and thank you.
Thanks.
Felix, thank you very much for organization. It was very great. It was a very convenient system.
Thanks very much.
Yeah, well done.
It worked out well. I was kind of, there were some close calls, but it worked out very well.
Yeah, very well.
Yeah, thanks. I recorded the final. I will see how it works because it recorded just all the streams individually, and I want to make like one coherent version of it. But I got a lot of positive feedback of the last year's final video because the audio is so good compared to the live performance, where capturing audio is really hard in a lecture hall. So I hope to like combine the final into a nice version to share.
Yeah, we look forward
Thank
to
you.
seeing that, Felix, because it really is. I mean, it comes across so well.
Yeah.
Thank you again.
Nice.
And thank you, Gavin,
It was
for all
fun,
your work.
Yeah. Thanks to Gavin, Kent, and the flight assistants.
Absolutely, the flight assistants.
Yeah.
Okay, time for bed.
Absolutely.
Or lunch.
Or lunch, wherever people are.
Yeah.
Bed.
I can see Alexander bathed in sunshine. Yeah.
Yeah. Time to be with family because now it's 3 p.m. Sunday, and all the vacations I was online and not with my family.
Fantastic. All right. Bye, everyone.
Yeah.
Bye.
Bye.
you.